Hello everyone, welcome back. So let us start. Just quickly recall in the last two previous classes I have just defined what is homomorphic encryption and then types of homomorphic encryption. We saw there are four different type of homomorphic encryption: partial homomorphic, somewhat homomorphic, labeled homomorphic, and then fully homomorphic encryption. Okay, so I have covered some partial homomorphic encryption. So today let us see before 2009 there was no fully homomorphic encryption scheme. So in 2009 first time this fully homomorphic encryption scheme was announced. Now we are here in 2009. It was given by Gentry. Okay. What he did, what was his idea actually? He has first given a somewhat homomorphic encryption scheme and then convert this somewhat homomorphic encryption into fully homomorphic encryption. Recall, as I told you, what is somewhat homomorphic encryption? That means it can perform only a subset of circuit. Then why it was? Because every time there will be some error will be added, and at some point, if we try to decrypt, then you won't be able to decrypt because there will be the threshold errors, something like this. Suppose earlier I was having this error, I'm just putting it as error meter. This is my message plus the error. You apply something, you apply f of m something, then this error will go somewhere on the top, correct? And again you apply something, then this error will be something like this. Phi of m, then it will be error will be something here. So after that, if you apply any of the operation, then this error meter, this error will be up from the threshold. Then if you try to decrypt, you won't able to get the correct value. Correct. So I will able to apply only till this operation. So that's why it was called somewhat homomorphic encryption scheme. Then by some method, by some criteria which is called bootstrapping, we are going to convert our somewhat homomorphic encryption scheme into fully homomorphic encryption scheme. Gentry has given this idea of making fully homomorphic based on ideal lattices. Okay, so what we are going to do today we are going to see a somewhat homomorphic encryption scheme over integers, and then we'll make it fully homomorphic encryption scheme, which was again, see, till now any FHE scheme is every FHE scheme that is and has been created, it is based on Gentry's blueprint. What do you mean by this? That means in all the cases you want to make a FHE scheme, you first construct a somewhat homomorphic encryption scheme, and then by bootstrapping method you convert it into fully homomorphic encryption scheme. This is your Gentry's blueprint. Every homomorphic encryption scheme will be made by this only. In all the cases you need bootstrap. So let us quickly see the physical analogy of this. What was the Gentry's idea behind this? How did he do that somewhat homomorphic, and how did he convert fully homomorphic? So as I told you that what we are doing in the case of FHE, we are going to compute on encrypted data. So let us have a real life example. Suppose Alice is there, and Alice has so many raw gold, and she would like to uh, she would like to make necklace of it. But the thing is that she cannot do this. She cannot construct this necklace by herself. So she is going to appoint some worker, some jeweler who is going to work on this gold and then get the necklace. Now the thing is that Alice cannot blindly trust on the worker because they may steal the gold and then they may use wrong gold or something like that. They can change the value, change the data here, correct? And so, or they can take this necklace away with them. So in this case, Alice don't want to give the, this is the data Alice is having, correct? And but she want to make use of this gold and make the necklace. That is the aim. So what is the homomorphic property here? Alice would like to compute this necklace, correct? But she don't want to give its message. This is my plain text. So what she will be doing, she will be giving encrypted of this, and then she want the necklace should be also encrypted. So for that, Gentry has given this idea, glove box. So what is this glove box? First, yeah, first raw gold material will be here. Alice will be keeping its gold here inside this, and some instruments also to make it make a necklace with this. Okay, and she will be putting this gold and say some hammer and whatever the requirement is there, everything she will be putting here. Okay, and then she will lock it. She will put this lock whatever here. I'm just denoting it like this. Suppose she is going to lock it with a key, and she will be having the key. Secret key is the key she will be having. She locked it. Okay. Now she will ask the workers what the worker will do. They will keep their hand inside this glove box and they will make the necklace with the all the thing with the gold and everything whatever they required. Everything in the glove. Everything is there in the glove box. So what do you see? In this case, your Alice. What was the aim of Alice? With raw gold, she wanted to make necklace, correct? But the case was she don't want to give this raw gold directly to the worker. So what she did, she made this glove box. She put her raw gold plus some instruments also to compute. Okay, and then she locked this. She locked this thing. Okay, and then yeah, the worker will come and with the glove box he will be putting his hand inside and he will be doing it and he will convert the necklace here for the Alice, and at last Alice will decrypt and get the result, get the necklace. Okay, so this is a physical analogy of fully homomorphic encryption scheme where you are performing on encrypted data and you are safe. So two things as I told you, privacy and correctness, that has been achieved here. Why privacy? Because the worker won't able to take any gold or he won't able to steal this gold because of this this glove box. Okay, and what is correctness? That means the final outcome should be a necklace. If he had ordered for the necklace, she should get necklace. She should not get something else, something ring or something else. Okay, that is your privacy and correctness. These two security notions are satisfied in this case. Okay, yeah. So this is going to be what your fully homomorphic encryption scheme is. Yeah, we'll come back to bootstrapping later on, maybe in the next class. So today, let me start with somewhat homomorphic encryption scheme. Over integers, as I told you. So this was given in 2011. Somewhat homomorphic encryption. Over integers. What do you mean by this? I'll just write somewhat homomorphic encryption over integers. SHEOI. This is a shortcut we will be using while referring to this. Okay, now let us see. Now let us first see symmetric keys. Symmetric key encryption. What is the difference between symmetric key and asymmetric key? Symmetric key, there will be only one secret, correct? And in the case of your asymmetric, there will be two keys. Here it will be only one keys, only one key for both encryption and decryption. Whereas in the case of asymmetric, or you also call it as public key crypto system, there will be two key. One key will be for encryption, and encryption key will be publicly available, and the decryption key will be secret. Okay. So now let us see in the case of symmetric key what happens. How does this somewhat homomorphic encryption works? How does it start? First thing is key generation. Here the secret key is an odd integer. Secret key is odd integer chosen from some interval. Say your secret key is P. Sorry, this is already, it belongs to some interval, say 2 raised to. Forget about this interval, because based on the security notion, these intervals are mentioned. Okay. This is your secret key. I am having only, as I told you, in the case of symmetric key, there is only one secret. So key generation. And what is encryption? In the case of encryption, suppose I am having a message which is a bit, either 0 or 1. Okay, I'd like to encrypt this. So what will be your ciphertext? Your ciphertext is equal to P into Q plus 2R plus M. Okay, where integers Q and R are chosen randomly. Okay, again in some prescribed intervals. In some prescribed intervals, so that such as your 2R, this guy, 2R is smaller than P by 2. You have to choose your R such that your 2R should be smaller than P by 2 in absolute value. Otherwise your decryption will fail. Otherwise, if you decrypt it, you won't get the message. We'll come back to that, don't worry. This is the encryption, basic encryption scheme. Suppose this is my message, and what I am going to add, I am going to add something and something. The first part is key dependent part, because it depends on your key. I'll write it as key dependent. Second part, it is called noise. This is the extra noise which we are adding, and the third part is your message. If you see any FHE scheme, fully homomorphic encryption scheme, will follow this technique mostly. That is, the first part will be key dependent part, which will be added with the noise, and then your message will be added. With this reason, this is your encryption scheme. And how do you decrypt? Decryption is again very simple here. You observe. For decryption, you just find your message by taking C modulo P and then modulo 2. What do you see? This is your ciphertext. If you take modulo P, this part will go away, and then if you take modulo 2, this part will go away, and then you will get the message. That means for decryption, there are only 3 steps. The first is by using key, remove the key dependent part. By using key, remove key dependent part. And second is remove the noise. See, I wrote 2 into R. 2 into R. How do I remove the noise? Just by taking modulo 2. Okay, this is our message. Remove the noise. Okay, and if you want to verify the correctness, is very easy. Modulo P and then take modulo 2. Now let us see whether it is satisfying homomorphic property or not. Suppose again I am having 2 messages, say M1 and M2, and say ciphertext C1 is equal to, what was the definition? P into some Q1 plus 2 into R1 plus M1, and here it will be C equal to P into Q2 plus R2 plus M2. Okay, now if I add to ciphertext, what I am getting? I will be getting P into Q1 plus Q2 plus 2 into R1 plus R2 plus M1 plus M2. What do you observe? Which is equal to say P into some other Q dash plus 2 into some R dash plus M1 M2. This is a encryption of addition of M1 M2, correct? I am just adding the ciphertext. I am getting the encryption of addition of messages. This is perfect. What about multiplication? If I multiply C1 into C2, if you see PQ1 plus 2R1 plus M1 multiplied with PQ2 plus 2R2 plus M2, if you multiply, you will see that if I multiply, there will be some term which is having P everywhere. There will be some term which is having multiplied with 2 everywhere, and at last there will be one term which is M1 into M2. And again, this is true in the case of decryption. I will be taking modulo P, this part will go away. I will be taking modulo 2, this part will go away, and then I will get the message M1 into M2. Correct? So that's why it is satisfying both homomorphic addition and homomorphic multiplication. Now, why this is somewhat, that is the question. Yes, okay. If you observe, there is a condition which I told you. This, what is your ciphertext, C is equal to PQ plus 2R plus M. I told you that your 2R part should be less than P, or I have written R is less than P by 2, whatever you say. Yeah, this noise 2R part is less than P by 2. Should write like this. Why this is true? Let us see. Modulus of 2R should be less than P by 2. That means this noise part, your noise should be less than modulus by 2. Your modulus number, whatever that number is, divided by 2. This is the condition. What see, after every time there is noise that is growing all the time. See, in the case of I am adding 2 ciphertext, what do you observe? Your noise is now R1 plus R2. Earlier it was just R or R1. Now the noise has been actually doubled. It is R1 plus R2 and multiplied by 2. Whereas in the case of multiplication, this noise will be again very high. So So there may be a case that this noise may cross this guy, cross the p by 2. Then the problem occurs. That means I can solve this. This homomorphic encryption scheme will work properly only if this noise part, this is less than p by 2. So this is the restriction what I am having. Correct? That's why it is called somewhat homomorphic encryption. That means this scheme can say this scheme can be only used to evaluate low degree Boolean function. Low degree Boolean function over encrypted data. Perfect. Okay. So we have to choose some parameters so that this should work. So there are some parameters defined which we can later on see. Now let us see security. What is the security for this? Why this scheme is secure? So this scheme can be reduced to the hardness of approximate integer greatest common divisor problem. Approximate integer greatest common divisor. That is also called approximate GCD problem. Approximate GCD problem. Okay. Yeah. So what is the approximate GCD problem? To give you a simple example, suppose I am having two number A and B. You can easily calculate GCD of A and B. Correct? Now if I add some error to this A and B, say A plus some key 1 and then B plus some key 2, very small error, then can you still get the GCD of AB by using these two? That is the question. This is a hard problem. Correct? You cannot do that. And then again there was some problem with this the security. That means how much security should be there for approximate GCD problem. See, for any hard problem there is some security analysis, because even if you take integer factorization problem, if you take small number then it is easily factorizable. Correct? So there should be security notion some 512 or 1024. If you take that much bit, then this will be secure, something like that. And this approximate GCD problem is believed to be hard problem in lattice theory. This is hard in lattice theory. So it is post quantum secure. So this is post quantum. This is quantum secure. So we call it as post quantum. So if you say there was a paper which says that if you take any R which is 2 raised to root of n and your q should be 2 raised to n cube, then the secret key somewhat homomorphic encryption scheme over integers, it's secure, easy and secure. This is the security path. This is the condition. If you follow, then this secret key somewhat homomorphic encryption scheme is still secure. Okay, I'll just quickly recall what are the things we have done. Then in the next class we will be doing the public key case. Suppose I am having public key, that is asymmetric key system. Then what happens? Here I was having only one key, that is P is the only key I am having. Message M is given. So what is the ciphertext? P into Q plus 2R plus M. The first part is key dependent. This is noise and this is message. And in the case of decryption, I am taking C modulo P and then modulo 2. This is my message what I am having. And I saw the homomorphic property, I add, I multiply. Then what do I observe? This first of all, I observe that this decryption is possible only if your noise part is less than P by 2. So that means I can perform only low bit Boolean circuit. Correct, low bit Boolean function, because suppose I am adding to ciphertext, what do you observe? The error is now 2 into R1 plus R2. I have to make sure that this guy should be less than P by 2. If that is less than P by 2, then this can be decrypted perfectly to M1 plus M2. And if I multiply, then you see it has so many terms, so I have to make sure whether everything is under this bound. So that's why it is called somewhat homomorphic encryption. I cannot solve for any function here. Okay, and the security is based on approximate integer GCD problem. And what is that approximate GCD? A simple way, if you see, suppose you are doing two numbers, then you can calculate GCD. If I have some error, then it is hard to get the GCD. Okay, so in the next class I will be doing that public key version of this. Okay, thank you.